All right, in this podcast, I'm going to review the last 3 questions on the Big Idea 2 free response questions. All right, so here is number 9. Says alcohol dissolves in water to give a solution that boils at a lower temperature than pure water, which means it evaporates quicker. And salt dissolves in water to give a solution that boils at a higher temperature than pure water. So you're going to have to give it a little more heat to get it to boil. Explain these facts from the standpoint of vapor pressure. All right, so what we're really talking about here is water has hydrogen bonding. Both solutions are going to have water in them. So I put up a picture of water. You see that molecules are hydrogen bonding. You have the oxygens aligning with hydrogens on other molecules and so forth. And then over here you just have alcohols. All right, well, what's going to happen is these alcohols are going to actually fit in the spaces in between the water molecules where they are hydrogen bonding, and it's going to interfere with that hydrogen bonding. It's going to weaken it, which is going to allow it to boil quicker. You have less of an impact with the IMFs because they are being disturbed by the alcohols coming in there. All right, salt gives a little different perspective. Salt is going to break into positive and negative ions. If it were NaCl salt, you'd get a Na plus and a Cl minus. What this is going to do is it's going to cause the molecules to align in a certain way around them. So you see here on the Cl minus, you'll get all of the hydrogens aligning towards it because the hydrogen has a partial positive charge in the water molecule. And then sodium, the positive ion, is going to be surrounded by a bunch of oxygen molecules which have a partial negative charge in the water molecule. Okay, this is going to involve a ion-dipole interaction. So water's polar, it can dipole. And then chlorine and sodium are ions in this situation, and an ion dipole is the strongest IMF you can have. It's stronger than a hydrogen bond. It is super strong interaction. So that means that they're going to want to stay together. They're not going to want to boil, so you're going to have to give more energy to that solution to get it to boil. Okay? All right, number 10 is talking about basically the 4 types of bonds that we have talked about: solids, ionic, metallic, covalent network, and molecular. Basically wants us to talk about the differences between these and then how we could identify each in the laboratory. All right, so we're going to go in order. Ionic, you get the positive-negative alternating lattice, very strong interaction. Metals, you get these positive core, the positive core of the metal, and then the electrons really aren't assigned to any specific atom. They just kind of float all around in a sea. Covalent network is the strongest that we have talked about. You have covalently bonded molecules that are covalently bonded to other covalent molecules, and then that's covalently bonded, so it's like super strength covalently bonded here. Diamond is the greatest example of that. And then you get molecular. Molecular is what we're talking about when we're talking about IMF interactions. You know, like here you see an example of a dipole or a hydrogen bond here. So that's what we're talking about with those. We're talking about covalent molecules and the interactions they can have between each other when we say molecular. Okay, so how could we identify each of these in the laboratory? All right, well, we know that all of these have differing strengths depending on the type of interaction. We know that covalent network is the very highest you can get. Then comes ionic bonding, then metallic bonding, and then last, molecular, where you get the IMF forces playing in there. Hydrogen bonding, dipole. Okay, so how could you identify these? I think melting point or boiling point would be a great one. This one is going to be super high, this one's next, and this one's the lowest. So you could arrange them in order of melting point, and that would give you a great perspective on it. All right, and the last problem, we are given some information about an unknown compound that has these 3 elements, and we need to determine the empirical formula. All right, so we know that we have a 65.6% is carbon. Should have known my little computer was going to do that. Okay, so 65.6, and we're just going to assume we have a 100-gram sample here, so we're just going to change the percentage straight to grams. Okay, so this is just carbon. All right, and then we have a 9.44%, or 9.44 grams. That's just hydrogen. And if we add these two numbers up and subtract from 100, we will be able to determine the amount that is the remaining element, oxygen. So let's see, 65.6 plus 9.44 gives us 75.04, and then 100 minus 75.04 is 24.96. So 24.96 grams is just oxygen. Okay, now we're going to convert all these to moles. Okay, so that just basically means we're going to be dividing by the molar mass here. So we're going to go ahead and divide by the molar mass of carbon, molar mass of hydrogen, which is 1.0079, and the molar mass of oxygen. All right, and then we're just going to plug all those in the calculator, get the values. So 65.6 divided by 12.011. See, that's a 5.46. Okay, and that'd be moles. I'm not going to write the unit, but know it's moles. All right, and 9.44 divided by 1.0079 is 9.36. Okay, and lastly, 24.96 divided by 16 is 1.56. All right, and that's all moles. All right, and then we would divide by the smallest, which is 1.56. This one's easy, it's 1. All right, and we're going to plug these in. So we got 5.46 divided by 1.56. That's 3.5, and 9.36 divided by 1.56 is 6. Okay, now you know you have a 0.5, got to get rid of that. So 0.5 is the same as a half, and we're going to multiply by the denominator, which is 2. So all these get multiplied by 2. So we got 2, 12, and 7, and those become the subscripts of our equation. So we got C7, H12, O2, and that's all you got to do for those.